Chapter 9, BJT and FET Frequency Response. General Frequency Considerations. The frequency response of an amplifier refers to the frequency range in which the amplifier will operate with negligible effects from capacitors and device internal capacitance. This range of frequencies can be called the mid-range. At frequencies above and below the mid-range, capacitance and any inductance will affect the gain of the amplifier. At low frequencies, the coupling and bypass capacitors lower the gain. At high frequencies, stray capacitances associated with the active device lower the gain. Also, cascading amplifiers limits the gain at high and low frequencies. 2. Bode plot. A Bode plot indicates the frequency response of an amplifier. The horizontal scale indicates the frequency, in Hz, and the vertical scale indicates the gain, in decibel. 3. Cutoff frequencies. The mid-range frequency range of an amplifier is called the bandwidth of the amplifier. The bandwidth is defined by the lower and upper cutoff frequencies. Cutoff, any frequency at which the gain has dropped by 3 decibels. 4. BJT amplifier low frequency response. At low frequencies, coupling capacitor, CS, CC, and bypass capacitor, CE, reactances affect the circuit impedances. 5. Coupling capacitor, CS. The cutoff frequency due to CS can be calculated by where? 6. Coupling capacitor, CC. The cutoff frequency due to CC can be calculated with where? 7. Bypass capacitor, CE. The cutoff frequency due to CE can be calculated with where? And 8. BJT amplifier low frequency response. The Bode plot indicates that each capacitor may have a different cutoff frequency. It is the device that has the highest lower cutoff frequency, FL, that dominates the overall frequency response of the amplifier. 9. Roll-off of gain in the Bode plot. The Bode plot not only indicates the cutoff frequencies of the various capacitors, it also indicates the amount of attenuation, loss and gain, at these frequencies. The amount of attenuation is sometimes referred to as roll-off. The roll-off is described as decibel loss per octave or decibel loss per decade. 10. Roll-off rate, decibel/decade. Decibel/decade refers to the attenuation for every 10-fold change in frequency. For attenuations at the low frequency end, it refers to the loss and gain from the lower cutoff frequency to a frequency that is 1/10 the cutoff value. In this example, FLS equals 9 kHz gain is 0 decibels. FLS/10 equals 9 kHz gain is minus 20 decibels. Thus a roll-off is 20 decibels/decade. The gain decreases by minus 20 decibels/decade. 11. Roll-off rate, decibel/octave. Decibel/octave refers to the attenuation for every 2-fold change in frequency. For attenuations at the low frequency end, it refers to the loss and gain from the lower cutoff frequency to a frequency 1/2 the cutoff value. In this example, FLS equals 9 kHz gain is 0 decibels. FLS, 2 equals 4.5 kHz gain is minus 6 decibels. Therefore the roll-off is 6 decibels/octave. This is a little difficult to see on this graph because the horizontal scale is a logarithmic scale. 12. FET amplifier low frequency response. At low frequencies, coupling capacitor, CG, CC, and bypass capacitor, CS, reactances affect the circuit impedances. 13. Coupling capacitor, CG. The cutoff frequency due to CG can be calculated with where? 14. Coupling capacitor, CC. The cutoff frequency due to CC can be calculated with where 15 bypass capacitor, CS. The cutoff frequency due to CS can be calculated with where 16 FET amplifier low frequency response. The Bode plot indicates that each capacitor may have a different cutoff frequency. The capacitor that has the highest lower cutoff frequency, FL, is closest to the actual cutoff frequency of the amplifier. 17. Miller capacitance. Any PN junction can develop capacitance. In a BJT amplifier, this capacitance becomes noticeable across the base collector junction at high frequencies in common emitter BJT amplifier configurations. The gate drain junction at high frequencies in common source FET amplifier configurations. These capacitances are represented as separate input and output capacitances, called the Miller capacitances. 18. Miller input capacitance, CMI. Note that the amount of Miller capacitance is dependent on interelectrode capacitance from input to output, CF, and the gain, avenue. 19. Miller output capacitance, CMO. If the gain, avenue, is considerably greater than 1, then 20. BJT amplifier high frequency response. Capacitances that affect the high frequency response are junction capacitances, CB, CBC, Cs. Wiring capacitances, Quo. Coupling capacitors, CS, CC. Bypass capacitor, CE. 21. Input network, F high, high frequency cutoff. Where and 22. Output network, FO, high frequency cutoff. Where and 23. Or comma variation. The parameter, or comma of a transistor varies with frequency. 24. BJT amplifier frequency response. Note the highest lower cutoff frequency, FL, and the lowest upper cutoff frequency, FH, are closest to the actual response of the amplifier. 25. FET amplifier high frequency response. Capacitances that affect the high frequency response are junction capacitances, CGS, CGD, CDS. Wiring capacitances, Quo. Coupling capacitors, CG, CC. Bypass capacitor, CS. 26. Input network, F high, high frequency cutoff. 27. Output network, FO, high frequency cutoff. 28. Multistage frequency effects. Each stage will have its own frequency response, but the output of one stage will be affected by capacitances in the subsequent stage. This is especially so when determining the high frequency response. For example, the output capacitance, Co, will be affected by the input Miller capacitance, CMI, of the next stage. 29. Multistage amplifier frequency response. Once the cutoff frequencies have been determined for each stage, taking into account the shared capacitances, they can be plotted. Note the highest lower cutoff frequency, FL, and the lowest upper cutoff frequency, FH, are closest to the actual response of the amplifier. 30. Square wave testing. In order to determine the frequency response of an amplifier by experimentation, you must apply a wide range of frequencies to the amplifier. One way to accomplish this is to apply a square wave. A square wave consists of multiple frequencies. By Fourier analysis, it consists of odd harmonics. 31.